Okay, so in fact, let's start with this example question. So we have this smooth tabletop, okay, and on top of this we have kept one block like this, and there is also a pulley over here. So the block is connected via a thread which is going around the pulley, but now the other end of the thread is actually connected to the axle of another pulley. Okay, and that pulley now has a system of blocks going around that one. Okay. So we have a situation like this. This pulley is of course fixed to this corner over here, and this is a smooth surface. Now what is happening is there's another system of couple of blocks here which are connected to a thread going around this pulley. So a situation like that. Okay, and we release the system from rest. So we have to find the acceleration of various blocks. Okay. So let us say this is block A, this is B, and this is C, and this is a smooth surface. So given the various masses, let us say this is 5 kilograms, mass of B is say 3 kilograms, and mass of C is 2 kgs, and G is 10 meters per second square. We want to find the accelerations of each of the blocks. So in case you have gone through, this is similar to one of the solved examples in H.C. Verma, but we'll be doing this question from basics over here. Okay. So just take down the question, we'll discuss more about it. Obviously, you have to consider both the threads to be massless and inextensible, and also both the pulleys to be smooth and massless. So everything is standard in that relation. Okay. So the first thing what we understand here is that if this pulley, if I'm labeling it as suppose P1, okay, then this pulley will have the same downward acceleration as the horizontal acceleration of the block. Yes, Rachit, we have completed Newton's laws of motion conceptually, but we have to learn certain types of applications. So it will take a couple of more lectures before we move on to friction. Okay. So let us say this acceleration is A. So that is the same acceleration as P1. So the first thing we have to understand here is that the downward acceleration of pulley P1, okay, in the ground frame with respect to ground has same magnitude as the horizontal acceleration of block A, and let us say that is small. Okay. Now the next thing we have to figure out here is that what is the motion of B and C like. Okay, so for that what we have to understand is that the motion of B and C, okay, if you look at that, if you look in the frame of the pulley P1. Okay, what will happen? The block B has a downward acceleration which is equal to the upward acceleration of block C. Okay, so let us say this acceleration is A prime. Okay, so this is the acceleration of B and C relative to the pulley P1. So let's say that is A prime. So B is coming down with an acceleration A prime and C is going up with an acceleration A prime, but this A prime is relative to the pulley P1. So this is a very important point to understand about the system over here. Okay. That see what is happening, the thread length between B and C, that's a fixed length. So with respect to the pulley, if the block B comes down with a certain distance, C has to go up by the same distance. So with respect to the pulley P1, if the block B has a downward motion, the block C has an identical upward motion. Hence these two A primes are same, but they are relative to the pulley P1. And the pulley P1 is which type of frame? It is an accelerated frame. So it is a non-inertial frame. So this A prime that we are writing, that is the acceleration of the blocks B and C in the non-inertial frame of the pulley P1. So that's how we have to solve this. Okay, so that is the first important concept over here, that when we write the acceleration of the blocks B and C, we have to first visualize that acceleration in the frame of this pulley P1, because in that frame what is happening, the downward motion of B is identical to the upward motion of C. Imagine you are standing on the pulley P1, so what you will see, the amount of distance B moves down, the same distance C is approaching you upwards by. Okay, whereas in the ground frame the situation is a little bit different. Okay, so now let's make the free body diagrams. Okay, so again coming back to the free body diagrams, let us say the tension in this string is suppose T1, okay, and the tension in the second string is suppose T2. So what will happen is, the first thing we'll do is the relationship between T1 and T2, because the pulley P1 is massless. Okay, that thing we had learned in the last lecture, that will come into play. So now let us look at the free body diagrams. Okay. So firstly you look at the FBD of pulley P1. So pulley P1 is massless. So even though it has a downward acceleration A, it does not matter because it is massless. So that means the net force on it must be 0. So what is the net force on it? There is tension T1 acting upwards, and there are the two tensions T2 and T2 acting downwards. Okay, so because of this, now what is happening, T1 must be equal to 2T2. Okay, so this is our first equation. So what we'll do here is that we'll say that let T2 is equal to T, therefore T1 is becoming 2T. So that is our first important equation, that the relationship between the tensions is like this. Okay, so make a note of this first. This of course with respect to ground frame only. Now similarly, next we will make the free body diagram of the block A. Okay, you have not written down the question? Okay, so finish writing down the question first, people. Okay, then we'll move on to the further free body diagrams. Okay, so finish writing down up to here, and next make the free body diagram of A. If you finish this, make the free body diagram of the block A. Okay, so I'll just take you to the full diagram once more so that you're clear about all the tensions and things. Okay. Right, so based on this, now let's make the free body diagram of the block A. So A is pretty simple for us. There is weight of A, which is getting balanced with normal reaction, so no problems there. And only one horizontal force tension T1, which remember is 2T because we just labeled that over here. That T1 is 2T and T2 is T. Okay. So that much tension acting on it, giving it a horizontal acceleration E, and this is in ground frame. Okay. So this is in the inertial ground frame. Okay. And mass of A, you remember, was given to us as 5 kg. So the important equation that we have, the horizontal one, T1 is equal to mass of A into its acceleration. So we can write T1 as 2T and that will become equal to 5A. So this is our important equation. Okay, this one. And of course we have a supporting equation that normal reaction on A will balance its weight. So this is not really that important for us because it's pretty obvious that the normal reaction will become 50 newtons. Okay, so this is clear, I hope. Now next we will move on to the free body diagrams of B and C. But the thing is, remember, B and C is acceleration, and the A prime acceleration that we've written, that is in what frame? That is in the frame of pulley P1. So remember this downward A prime of B and the upward A prime of C, that is in the frame of the pulley P1. It's relative to P1, and P1 is a non-inertial frame because it's moving down. Okay, so we have to make the free body diagrams of B and C in the non-inertial frame. So next thing we'll see is the free body diagrams of B and C are drawn in the pulley P2's frame, or sorry, the pulley P1's frame. And that is what kind of a frame? That is a non-inertial frame which has a downward acceleration of A. Okay, so that is the first thing over here. So that our non-inertial frame of pulley P1, this is having this downward acceleration of A. So for example, when we make the block B's free body diagram, this block in this frame is coming down with an acceleration of A prime. Okay. A prime is the downward acceleration of the block B with respect to pulley P1. Okay, this thing. Okay. Now of course, what are the forces acting on it? So there is tension T2 acting upwards, which we had labeled as T earlier, and then of course there is the block's own weight acting downwards, and the mass of the block was given to us as 3 kg. So we have one equation for this, that is, and of course there is most important pseudo force. Okay. Now pseudo force kaisa hoga? It will be upwards because A is downwards. So this will be mass of B into acceleration of the frame. So this is our pseudo force which is acting upwards. Okay. So what is the equation for this now? The net downward force is weight minus T2 minus pseudo force. That should be equal to mass into acceleration in this frame. So substitute the mass as 3 kg. So 30 minus tension T2 is equal to T minus 3A is equal to 3A prime. So this becomes the important equation for us. So this becomes our third equation. Okay. So I'll just minimize this a little. So make sure you have got the three equations till now. Okay. And finally make the free body diagram of the block C also in the non-inertial frame. So note this down and make the FBD of the third one yourself. Tej, you again want to write the sum from the start? I thought you finished with the question. Okay, now let's come to the third block's free body diagram, the block C. So you can see in the original diagram what is happening to C. C is going up with an acceleration A prime relative to the pulley P1. Okay, so you make the free body diagram of the block C in the frame of the pulley P1 again, but the difference is this time it is going up with that acceleration A prime. B is coming down, this one is going up. Okay, I'll just wait for you to write this down. Okay, so if you finish writing all this down, then please make the free body diagram of the third block C and come up with the fourth equation. So see, the unknown quantities for us are T1, T2, A and A prime. Okay, so we have four unknowns. So we require four equations. Three of them we have got. Now the fourth one will come from the free body diagram of the block C. So just make that yourself and try to come up with the equation. Then we'll solve them. Yeah, so Vashish, if you finish, now solve them to find out A first. Okay, so solve the equations first of all to find out the acceleration A, and then solve A prime. And from that we will get the acceleration of each of the blocks in the ground frame. So let's come to the free body diagram of the block C. So this one also we'll be making in the non-inertial frame of the pulley P1, which is going down with that acceleration A. So in this frame, the block C, which had a mass of 2 kg, so in this frame it has a relative acceleration of a prime upwards. Okay, so a prime is the upward acceleration of the block C with respect to the pulley P1. Okay, that is that a prime. Okay, now the forces acting are, there is the tension T2, which we've already labeled as T, but there's also pseudo force. So this is the pseudo force, and of course there's the block's own weight, and this time is going up. So we'll write the net force as the upward force. So T2 plus the pseudo force minus the weight of the block should be equal to mass into acceleration in this way. So this will become T2. So T2 we'll write as T, sorry. So we'll directly write this as T. So T plus 2a, okay, minus 20 is equal to 2a prime. So this is going to become our fourth equation. No, pseudo force will be up, no, beta, because pseudo force is opposite to acceleration. Remember, the pseudo force is given by the formula. It is minus of mass of the object into acceleration of the frame. So here acceleration of the frame is downwards, so pseudo force will be upwards. Acceleration of the pulley P1 is downwards, so pseudo force should be upwards. अरे acceleration of the block नहीं बेटा, acceleration of the frame. A naught क्या होता है? It is the acceleration of the non-inertial frame. So here the acceleration of the non-inertial frame is A downwards. Yes. Okay. So you have to be very careful. Don't confuse the acceleration of the block with the acceleration of the frame. Which is why I've written very carefully for you which one is which. E prime is the acceleration of C with respect to pulley P1. Whereas frame का acceleration क्या है? A downwards. Okay. So now let's get down to solving the equations. So T1 is equal to 2T2. I have already made use of this equation. I have taken T2 as T and T1 as 2T. So that's made use of. Okay. Now the second equation was that 2T was equal to 5A. This was the second equation. Okay. Then the third equation was this one. 30 minus T minus 3A is equal to 3A prime. Okay. And this fourth one we just have right now, that T plus 2A minus 20 is equal to 2A prime. So now what we will do is, first we will, so we want to find out acceleration E. So first what we'll do is we will eliminate E prime between equation 3 and 4. Okay. So what we'll do is we'll take equation 3 and multiply it with 2. Multiply it with 2 and take equation 4 and multiply that with 3. Multiply the whole equation with 3. Okay. So left hand side of both the equations is same. So 6A prime on both the sides will become 2 times 30 minus T minus 3A, which is 3 times T plus 2A minus 20. Correct. So this will give us another equation. Okay, so see 60 minus 2T minus 6A is equal to 3T plus 6A. Okay, minus 60. So we'll have 120 minus 5t is equal to 12a. You will have this equation. And now in this equation, what we'll do is we will substitute the value of t from equation 2. Substitute t equal to 5 by 2a from equation 2. So that will give us the expression. And then of course we still have to calculate a prime. So on doing this substitution, yeah. So on doing this substitution, we'll get 120 minus 25 by 2a is equal to 12a. Yeah. So we'll get this. Okay. And then we can calculate the value of a prime. Yes, so this is approximately 4 point something. We rounded off to first place of decimal. Okay. So now from this we can calculate the value of a prime, for example. So we can substitute in this equation or this equation and we can calculate a prime. So 2a prime is equal to t plus 2a minus 20. So that means 2a prime is equal to 5 by 2a plus 2a minus 20. Okay. So that is, so a prime will come from this as, so we can make this calculation next. So this will come nearly equal to 1. It will come as 1.02 something meters per second square. So this will come nearly equal to 1 meters per second square. So this is what our E prime will come out to be, and this is what our E was. Now from that we will find the acceleration of each of the blocks. Okay, so now the very important thing to understand next is that in ground frame, what is happening is that this block, the one on top of the table, the block A, is obviously moving with the acceleration E, which we have already found out. It's about 4.9 meters per second square. Okay. But what is happening is that this other blocks, their situation is different. Okay. This pulley is coming down at 4.9 meters per second square. Now see what is happening is this block B, okay, the block B is coming down with respect to the pulley at E prime equal to 1 meter per second square. Okay, so it's like this. So we can understand like this, that the acceleration of the block B with respect to the pulley P1 is equal to minus j cap meters per second square, minus 1 j cap. Okay, if you take the y axis to be upwards, and the acceleration of the pulley P1 itself is how much? It is minus 4.9 j cap. So that means the acceleration of the block B in the ground frame itself will be E prime plus E in the downward direction, or it will be minus 5.9 j cap. So in the ground frame, this block will have a downward acceleration of E prime plus E. So that will be 5.9 meters per second square. So this is acceleration of the block B with respect to ground. Similarly, the block C with respect to ground, what its acceleration will become? Its acceleration will be downwards, but it will be E minus E prime. So it will be about 3.9 meters per second square. So similarly, what is happening to the block C? The block C has an upward acceleration of E prime with respect to the pulley P1. Okay. So what is happening in the case of C is the acceleration of C with respect to the pulley is plus A prime j cap, or plus j cap. Okay. Because E prime is 1. Whereas the acceleration of the pulley itself is minus a j cap, or minus 4.9 j cap. So the acceleration of C in the ground frame, it becomes plus j cap minus 4.9 j cap, or it becomes minus 3.9 j cap. Okay. So the block C has a downward acceleration of E minus A prime with respect to ground. Okay. So this is a very important concept to understand and apply over here. Okay. So finally, this is the situation. The acceleration of the block B is downwards, and it's equal to A prime plus A. The acceleration of block C is also downwards, but its magnitude is a minus a prime, whereas the acceleration of block A is horizontal and it's equal to a, which is 4.9. Okay. So just make a note of this properly, people. Okay, so later when you are revising this, you can go through a couple of examples from H.C. Verma which are very similar to this question. Okay, so in H.C. Verma there is solved example number 9, okay, which is on page 74, in which you can solve by a similar method. Okay. And then there is also one question in the exercise. Question 28 in the exercise. So both of these questions you can solve by a similar method. Okay, now we'll move on to another question relating pseudo force and this time also constraint relation. And after this one, we will come to your doubts in HC Verma. So keep a list of your doubts ready so we can discuss those questions. So next question for us. So we have this kind of a situation, a large rectangular kind of wedge with a pulley attached near the top. Now there's a smaller block attached over here. And a system of pulleys like this. So these two pulleys are attached to the fixed wall, whereas this third pulley is attached to the corner of this block, and this is a smooth surface. So given that the mass of this larger block is 10 kilograms and the small block is 2 kilograms and g is equal to 10 meters per second square, this system is released from rest with the thread taut, and all the surfaces are smooth, so even this surface is a smooth surface. So find the acceleration of each of the blocks. So let's work this question out quickly. let's understand the approach to this question in more detail first. So uniform magnitude of tension T acting everywhere in this. So now you'll see that in the ground frame, if this block has a horizontal acceleration of E1, okay, so E1 is the horizontal acceleration of the wedge capital M with respect to ground, okay, and this one has an acceleration E2, but this is relative to the wedge. So E2 is the downward acceleration of the block small m relative to the wedge. Okay, like that. Because see, what is happening is in ground frame, if you think about it, if this was here at some point of time, okay, then after some time, by the time this is reached here, this block is reached here. So this has an acceleration like this. It doesn't have a downward acceleration. Okay. But yes, if you're standing on the block, on the wedge, then your frame it will look like this is going down. So that's the thing. Okay. So the acceleration of the block small m in ground frame is not vertically downwards. Okay, it is this sort of diagonal direction, whereas the acceleration of the block in the wedges frame is downwards. Okay, so that's the thing to understand. Okay, so now based on this, you set up the free body diagrams and write the equations. Okay, so next step, what you do here is make free body diagrams, okay, of the wedge in ground frame, okay, of the block small m in the wedges non-inertial frame, okay, and also find the constraint relation between A1 and A2. You have to do that also, okay, and before you solve. So constraint relation you can get from thread length conservation here, because there's a single thread, so thread length conservation is very easy. So you can just try this out based on this now. Okay, so let's understand the forces on each of these. So let's start with the wedge. In the inertial frame, it has a horizontal acceleration a1. Okay. Now remember the pulley here is attached to it. So tension, tension, one horizontal tension here, and also there is a block it is pushing against. So the block will be applying a contact force backwards like this on it. Okay. And of course it has its own weight, capital Mg, and some normal reaction from the ground, let's say n prime. Okay. So counting together all the forces on it, there will be 2T acting horizontally, T acting vertically downwards, one normal contact force that the block is applying backwards, normal reaction that the ground is applying upwards, and of course the weight of the block, and it is having an acceleration E1. So this is the wedge, capital N. So its equation for the horizontal direction will become 2T minus N is equal to capital M A1. This is our first equation. Okay. And of course N prime balances capital Mg plus T. But this is not going to be of much use to us. This is the equation which will be of use. Now next up, let's make the free body diagram for the block, but that will be in the non-inertial frame. So the block is placed against the wedge like this, and we are looking at it in the non-inertial frame of the wedge. So that itself is accelerating horizontally at E1. So there's a pseudo force on it, small m A1, acting backwards. Okay. And that pushes it against the wedge, which gives it the normal reaction N. Tension T acting upwards, its own weight mg. And in this frame, it has a downward acceleration E2. So E2 is the downward acceleration of the block M relative to the wedge, capital. So this is the block M's free body diagram in the non-inertial frame. This is the wedge, capital M's free body diagram. in ground floor. Okay. So for this one, we have n is equal to small m a1. That is our second important equation. And the net force downwards, mg minus t, is equal to ma2. So this is our third equation. Okay. Now you can see that in the equations, our unknown quantities are tension, this n e1 and e2. So we have four unknowns. So we require a fourth equation for solving this also. So where the fourth equation will come from? The fourth equation will come from the constraint relation. So the fourth equation will be the constraint relation. Okay. So try to work out what will be the constraint relation. Meanwhile, I'll just substitute the values. Capital M was 10 kg, I think, right? And small m was 2 kgs, if I'm not mistaken. Yeah. Okay. So this equation will become 2t minus n is equal to 10a1. Then this one will become n is equal to 2a1, and this will become 20 minus t is equal to 2a2. Now, what is the relationship between a1 and a2? Can anyone tell me that? Just apply thread length conservation in the original diagram. You'll get it very easily. Constraint relation people here will be that E1 will be twice of A2. Let's understand why that will be the case. So let's understand how the constraint here works. So see, if at some point of time, this is the arrangement between the two blocks, and of course, so this is the situation at some instant. Now, a moment later, what would have happened is that the whole block would have shifted, the wedge would have shifted to this position now, somewhere here. Okay. And the block would have shifted to somewhere here in that time. So you can see that this has moved the same distance. This has moved the same distance as the wedge has moved. Okay. Whereas this has moved a downward displacement of y, let's say. Okay. So what happens here is as the block or as the wedge capital M moves x horizontally, okay, what happens? It releases 2x length of thread. Okay, यहाँ पे और यहाँ पे 2x length of thread gets released because this thread is here now. So this much length here and this much length here is released. So where that length is going, that's going here. So the block small m pulls down by length of thread. So because the total thread length is constant, so whatever thread length this one releases, this has to pull back the same amount of thread. Okay. So y has to be equal to 2x. So now double differentiate. So this one's relative acceleration a2 has to be equal to twice of this one's horizontal acceleration a1. This is the constraint relation. Okay, so a2 is equal to twice of a1. That is the constraint relation. Understand also that okay, there are two horizontal tensions acting on this. So this is moving with v1. You can also understand by virtual power method. So plus 2t v1 is the power here. Okay. Whereas for the block, what is happening is there is tension T acting upwards and it has a downward velocity component of V2. So the power on the block is minus TV2. So net power must be 0. So 2TV1 minus TV2 must be 0. So V2 is equal to twice of V1. So from this also you can see you get this by differentiating. So you can apply the virtual power method also. Okay, so this is very important here, the constraint relation. And now we have to just solve these equations. Okay. So the constraint relation becomes our fourth equation. So I'll just list out the equations on the side so that we can solve them now. So we have 2t minus n is equal to 10a1. That is our first equation. And then let's write out the other equations. N is equal to 2a1. That's our second equation. And 20 minus t is equal to 2a2. That is our third equation. And a2 is equal to 2a1. That is our final constraint relation. So what we can first of all do is substitute this here. So this equation now becomes 2t minus 2a1 is equal to 10a1, or 2t is equal to 12a1, or t is equal to 6a1. Now substitute this in the third equation. So we'll get 20 minus 6a1 is equal to 2a2, and then substitute this over here. So substitute a2 as 2a1. So that will solve the situation. So 20 minus 6a1 is 2 into 2a1. So a1 will become 20 divided by 10, or 2 meters per second square. And a2 will become therefore 4 meters per second square. Okay, so just write down the solution. Now we'll come back to the acceleration of the block. Okay, remember we have to calculate the acceleration of the block in the ground frame. A2 is in the relative frame of the wedge. So we still have to calculate the acceleration of the block in the ground frame. So we'll come to that. But just note down the constraint relation also properly once. Okay, people. So hope the solving of free body diagrams and the final equations are clear. Now, just to work out the accelerations, so you can see that this block, okay, this string and all this is there. Now, this is going in the ground frame only at A1. So as far as the wedge capital M is concerned, it has an acceleration of 2 I cap horizontally like this only. So you take the x axis like this and y axis like this. But as far as the wedge is, the block is concerned, now for the block small m, what is happening is that it has this component of acceleration A2, but it also has this A1 because in the ground frame ultimately it's moving like this. Okay, so what is happening is that the acceleration of the block with respect to the wedge relative to the wedge, this one is minus 4 j cap. Okay, that is A2 downwards, whereas the acceleration of the wedge itself is nothing but 2 I cap. So the acceleration of the block in the ground frame becomes the vector sum of these two. It becomes the acceleration of the wedge with respect to the block plus the acceleration of the wedge. So it becomes minus 4 I cap plus, sorry, minus 4 j cap plus 2 I cap. So the ground frame acceleration has a horizontal component of 2 and a vertically downward component of 4. Okay. So this is the acceleration of the block with respect to ground frame. Okay. I'll show that to you in a vector diagram also, so things will be easier to understand. So what is happening is that the this is the A2 equal to 4. This is the acceleration of the block with respect to the wedge. Okay. This is on this side. Okay. And this is the acceleration of the wedge in the ground frame. Okay. So the net acceleration becomes the vector sum of these two. So this is the net acceleration of the wedge, sorry, of the block with respect to the ground plane. This one, this is this. Okay. So it has a magnitude of this much. Okay, so make a note of this, and next let's solve some of the questions from HC Verma. So if you have any doubts before question number 20, please drop a message first. Any doubts from HC Verma from question 1 to 20? Start with that. So finish writing this down and please send me the message with the doubts. I'll explain those particular questions. Okay, so we will start with question number 7, people, because that's the first one I've received as a doubt. So, okay. So it is basically talking about contact force. Okay, the sixth question also I'll come to that. Okay. So let me start with the seventh question. So I'll just make the diagram of the seventh question and it will be clear to you. So question 7, the situation is basically something like this. You have on a horizontal surface, you have a combination of two blocks kept against each other, and it says that the experimenter is pushing one of the blocks with a force like this. So the question that is asked here is, what is the force between A and B? Okay. What is the force that acts between A and B? So the answer to that is a normal contact force. Okay, the force that will act, the answer is that it is a normal reaction contact force. Let's say N, that will act in this manner. A will push B and B will push A backwards like this. So no numerical analysis is required, just this is required. So Abhi, you want to find out the force, na? So what you do is you assume the system has some acceleration A and just eliminate, na? So when you look at the free body diagram of the block E, you have Fn. So you have F minus N is equal to this. Okay. And when you look at the free body diagram of block B, you have only normal reaction force pushing it horizontally. So N is equal to mass of B into A. So now these two equations you just solve them, equation 1 and 2. So solving this, you will get acceleration as F upon ma plus mb. Okay. So substitute that in equation 2. You will get n is equal to mb into F upon ma plus mb. So that's that only. The way they've given the answer, that is only. Oh, I think there is a slight misprint. In the answer, there should be a division sign. Okay. So instead of F into that factor, it should be. So the correct answer is it is F divided by 1 plus ma by mv. This should be the amount of compact. So that division sign is missing. Just make a correction there. Oh, wait. The question is something else. It's not this. The question is reverse actually. The question is saying you have to find the value of F because that is the force by the experimenter in terms of N, the contact force. Okay. So it's actually reverse of this. So what we have to do is we have to find, in our equation we have written F as the external force. Okay. But what you have to do is you have to take this as some external force, suppose. Okay. So this is this external force. So now you have to find the value of external force given that the normal contact force is N, is F. Okay. So the language of the question is slightly different. You have to understand that carefully. So forget about this step now. Okay. So this is the relationship between the normal contact force and the external force. Okay. So this is the equation. Okay. Now the question is saying that if N is equal to F given, then find the external force that we are applying this. Okay. So just use this equation. So you can see that F external from here is equal to ma plus mb upon mb times n. So substitute the value of n as f. Substitute this thing here. So you'll get your f external as 1 plus ma by mb times f. Is it clear now? So this contact force's magnitude only is given to us in the question as capital F. So on the basis of that, we have to find the external force. So the question is kind of reverse. Okay. So write this down. Let's come to sixth question next. Yeah, Tej, I will send the notes very soon, so you'll get to write this down. Don't worry. It's a very simple question. I'm sure you'll remember also. Okay. Let's try to utilize the time we have in solving some questions at least. So question 6, I will give you a hint of what you have to do. So we देखो question 6 में क्या है? We are given the velocity versus time graph. So what does velocity versus time graph tell us? The slope gives us acceleration. Okay. So this sort of graph is given to us. So remember the slope, that is delta v by delta t, is the acceleration. Okay. And then of course the net force acting on a body is equal to mass into acceleration. Okay, so Shweta, you understood the point over here. So you have to use the graph to find out the slope. अभी देखो ग्राफ जैसा बना हुआ है, it looks to me like the velocity is becoming 15 meters per second after a time of 3 seconds. So यहाँ पे अगर acceleration a1 है, a1 will be 15 minus 0 upon 3 minus 0. So it should be 5 meters per second square. Okay. Here of course it's a flat graph, so this acceleration will be 0. Okay. And here it's decelerating, and it's decelerating from again this is 5 seconds and this is 8 seconds. So यहाँ पे a3 कितना हो जाएगा, a3 will be 0 minus 15 upon 8 minus 5, so it will be minus 5 meters per second. Okay, so these are the accelerations. Is this clear, Shweta, how to calculate the acceleration from the graph? Okay, and then you just apply Newton's second law once you know the thing, once you know the acceleration multiplied with mass, so you will get the force. Okay, now I will teach you about spring force in the next lecture. Okay, so you leave out question number 10 for the moment. Okay, I will ninth and 10th you just leave out. We will discuss about spring force in the next lecture. Question 8, let's discuss. Okay, so we will do spring forces. We'll discuss in the next lecture. Okay, now eighth question, let me give you an idea. So what is happening is that you have, let's say this is the surface of the head. Okay, now it looks very strange. Wait, see if I can draw this better. So this is the head surface for the bald man. Okay, and a raindrop like a sphere which is falling like this. Okay, so as the raindrop falls onto his head, as it just comes in contact, it has a downward velocity of whatever is given to us, 30 meters per second. Okay, and its mass is also given to us, 4 milligrams. Okay, now by the time the raindrop is coming to rest, what we are assuming is that, okay, it covers a distance equal to its radius on the head. So it becomes like this. So between this state and this state, the distance it covers, by the time the velocity becomes zero, the distance is equal to the radius, which is equal to 1 millimeter. Okay. So what we'll assume is that as it's coming in contact with the head, there is some kind of an acceleration like this. Okay. So if the average acceleration, actually deceleration, is a, okay, then final velocity should be initial velocity minus 2as, like this. So that average acceleration should be equal to v square by 2s. So 30 meters per second whole square divided by 2 into 1 into 10 raised power minus 3. So that average acceleration is 9 into 10 raised power 2 divided by, okay, so it is 9 into 10 raised power, sorry, 9 by 2 into 10 raised power 5 meters per second square. This is the average acceleration. Diti, I explained that I will discuss spring force in the next lecture. Okay, let's just concentrate on these few questions the time that we have today. Okay, so you will find the average acceleration like this. Okay. So the force will become mass into acceleration. So whatever force the head is applying on this now, this average force, that will become mass into average acceleration. So that will become 4 milligrams. So 4 into 10 raised power minus 6 kg into 9 by 2 into 10 raised power 5 in meters per second square. So this will give you the force. Okay, understood this? Okay, next up, let's come to 12th question. Okay, so 12th question is all about the free body diagram. So in question 12, what is happening is that the person who's inside the ditch, okay, I'll come to that also. Okay, now he's tied by two ropes, which you can treat like massless threads. So they are like this. Okay, so I have this kind of an arrangement here. So if these two people are pulling with force F each, by symmetry you will see they're pulling with the same amount of force. So that becomes equal to the tension in the string. Okay, so this person, now what is happening? He's moving very slowly. So the acceleration is tending to zero. So you take the person's free body diagram, and mg has to be balanced with two tensions which are equal in magnitude, which are acting like this. Now let us say this angle is theta. So if the upward acceleration is tending to zero because he's moving very slowly, so you can see that 2t cos theta should be equal to mg. And whatever force you're applying, that is only the tension. So that tension equal to the force is mg by 2 cos theta. So now the only thing is, how do we find out the cos theta? So for that, you can see the geometry of this triangle is given to us. This depth is given to us. It's h, and this whole distance from here to here, this is given to us as d. So in this triangle, you can see this will be d by 2, or in this triangle, this will be d by 2, and this is h. Okay, and this angle is theta. So we can replace cos theta with base upon hypotenuse. Okay, so substitute that here and you will get the force. So that is question number 12. Okay, next we'll come to question 15. Okay, so question 15 is about application of pseudo force. Okay, 19 also, okay, we'll discuss. So in question 15, see what is happening, that when the elevator is accelerating upwards, at that point of time, the pseudo force acting on the person will be acting downwards. So the weighing machine will read the normal reaction as the weight. So there's a person of mass m. Now this elevator is accelerating upwards. So that point of time, what is happening is that because he is in the non-inertial frame, going upwards with an acceleration a, there's a pseudo force acting downwards on his body. Okay. And that is interfering with the measurement of this normal reaction. So this normal reaction, let's say N1 in this case, is mg plus ma. Okay. And this N1 will correspond to the maximum reading of the weighing machine. Okay, which is 72 kgs or whatever. So N1 should be equal to 72 G. So your first equation is that 72 G is equal to this much. Okay, so this is your equation 1. Now similarly, at a point of time when the elevator is decelerating while going up, but with the same magnitude of acceleration. So at that point of time, the pseudo force acting on his body is acting upwards. So same situation for him. He's standing inside, but this time it's accelerating downwards or it's decelerating with the same magnitude. So this time the non-inertial frame will apply an upward pseudo force on his body. So this time the normal reaction that the weighing scale reads N2, this will be the minimum normal reaction, or this will give you the minimum reading. So N2 here will become mg minus ma, and this will correspond to the minimum reading of the weighing machine, which is whatever 60 kgs. Okay, so 60 G is the value of N2, which is m into G minus E. So now just solve equation 1 and 2 and you will get the value of whatever you require. Whether you're solving for M or you're solving for A or whatever, you get the value. Okay, so hope this question is clear. Okay, let's come to the 19th question now. Okay, so in 19th question, on a hot air balloon, there are two types of forces which are acting. Okay, one is the buoyant force, which is a constant force. So let's say this is your hot air balloon and you have suspended some mass. Now on this there are two forces acting. One is the buoyant force, okay, which is a constant force, and the other is air resistance. Now air resistance acts opposite to the velocity. So one time it is descending with a velocity which is uniform. So its acceleration is 0. So this time the air resistance force will be like this. Okay, let us say this is the so R is the air resistance force which is opposite to velocity, okay, and proportionate. Okay. So as a vector, it would be some minus some constant into v, or the magnitude would be some constant into v, but direction would be opposite. Okay. So there is that, and of course there's the weight of the block. So there is capital Mg, and acceleration is 0. So the equation that we are getting from here is that R plus B is equal to capital Mg. This is the first situation. Now in the second situation, what is happening is we are removing some mass from it. Okay. And now the same balloon is ascending with the same constant speed. So we've removed some mass, we've cut out some mass from this. So now this mass is m minus m prime, let's say. Okay. So buoyant force is acting in the same direction because it's a constant force. But this time it is going up with the same velocity. So this time what about the air resistance force? It is downwards. Okay. And of course weight is downwards. So acceleration is zero means that this time buoyant force is balancing the sum of the reaction force, air resistance force, plus this. So this is our second equation. Okay. So this time it is ascending at constant speed. Here it was descending. So the speed is the same in both the cases, but the direction is opposite. So the air resistance force direction reverses. Okay. Now just solve 1 and 2. Add equation 1 plus 2 and you will get the value of m and how much mass has to be removed. So hope you are clear with this question also. Okay. So with this we conclude today's session, people. Now next week also we'll discuss some more questions and obviously doubts from HC Verma. So please try to finish HC Verma's exercise, all 42 questions by next week, please. Make sure you attempt each and every question and keep the doubts ready for the next lecture. That's it for today's session, people.